Hi everybody, welcome back, and we're going to talk about heaps. But first I want to give another motivation for heaps as well as a quick addendum to the binary trees lecture. So what happens, if you can see this bottom here, let's do it over here. When you insert A into a binary tree, and then insert B, and insert C, and insert D, and because each one is successively greater, you create a big long list like this. Now this is bad because what happens is this creates an O of n operation instead of an O of log n. Now this is only in this one degenerate case. On the average case, log n, you're fine. But in the worst case where you accidentally put things in a sorted order or just happen to fall in a situation, you end up with a very long runtime, and that's no good. There are lots of ways to get trees to balance or to check on this condition, and if it occurs, balance the tree is the term for it by shifting things around. And we're not going to talk about any of them because it's actually a good motivation for heaps. So heaps don't have this problem because of the properties they impose, and heaps are one solution to binary balancing issue. But I wanted to mention that as a degenerative worst case scenario for binary trees. So now with heaps, a little motivation with that. Heaps are also called priority queues, and they are used, as we talked about in the queue situation, when you want a first in, first out data structure. First in, first out data structure, but you want some priorities in there. And this happens a lot. I'll give you a couple of quick examples in hospitals. So if you go into a hospital, you don't expect that you're going to be taken in the exact order that you arrive. A guy that's walking in with a gunshot wound should be taken first because he's a higher priority. And you expect that and you're okay with that. And it's important to note that it's not always the case that FIFO is the right way to go. Sometimes priorities are important. Also with task lists, like we all do, your boss calls up and says, do this now, becomes a higher priority, you interrupt what you're doing, you shift to that, and so forth. So having a priority attached to an item will push it up to the front of the queue and cause it to be the next thing that you tackle. And that's a very good and important thing to do in many situations. So heaps are binary trees, essentially, with two other important properties, restrictions, etc. And that is shape and order. So shape is a complete binary tree, not a full binary tree, but a complete one, which means that it's full down to the next up level from the one you're working on, and all the nodes are placed on the left in order, like this. So recall from the other lecture. So if we had a node here, this would not be a complete tree, and it would therefore not be a heap. It's very important that heap always maintain these properties. And you'll see the algorithms enforce these properties. And we also have a ordering restriction. The ordering restriction is that every node is greater in priority than all of its descendants on both sides. Unlike with binary trees where we did less than or greater than, with heaps it's greater than everything below it. So J is greater than all those things, greater than all those things. But it's actually not greater than, it's a higher priority than. And the reason why is because you can have a min heap or a max heap. A min heap is a heap in which the minimum priority is, the smallest number, the minimum number is the highest priority. Sorry, I said that backwards. So a min heap is the smallest number high priority, and a max heap is a highest number is highest priority. This is a max heap because we're doing letters, and J is higher than all those other letters. If we had an A up here, then it would be a min heap, because A would be the highest priority. Both are valid types of heaps, and you have to obviously know what you're working on in order to do the right comparisons, because otherwise the order property is flipped with respect to the particular nodes. There's only two operations in a heap, which are insert and delete. You really want to use a different type of data structure if you want other operations. So with binary trees, where we had a get, you can comparatively search down a tree for a data item. That's a binary tree thing, but not a heap thing. Because remember, this is an extension of a type of first in, first out queue. The only things we're interested in are putting something in and taking out the highest priority. Putting it in sorted by priority and taking out highest priority. And that's all we want to do. If you want to do anything else, then you're better off with a different type of data structure, most likely. Because you'll see, we're going to go through the operations. They operate on tree structures by moving down and up the same way. These are going to be order log n, just like binary tree operations are, which again is very, very, very quick. So what we've got here is a queue structure that now we don't have order 1 anymore, but now we have log n. But now we can queue priority, and in the cases where that's absolutely needed, you don't want to go back to a regular list where you have order n operations. You can at least go with something like a priority queue and support the single insert out and output operations, or input and remove. See, another thing about heaps is storage. Similar to queues, they're oftentimes stored in a static array. I wanted to go through that real quick because you'll see that come up. We're not going to go through the programming details of heaps, and we're not going to actually do a lab on them. But it's important to understand how they're represented in memory and how the algorithms will work. Because again, you're going to be tested on them, of course, but also so we have know that we've assessed the understanding so that you'd be able to do it if you were asked to do it in a programming environment. So what happens here when you're mapping these to arrays is you read them off basically left to right from top to bottom. So level 0j goes in the 0th position. Root always goes in 0. And then you take the next node down, H goes in 1, I goes in 2, and reading across. So D, G, F, A, D, G, F, A, B, C, E, B, C, E. That's only really useful if you're mapping in a graphical sense. Because the algorithms obviously are going to do different things with the array mapping. This makes it easy to calculate because you can actually use a formula on this. So this root is the 0th position, and what you do is you do 2 times the parent's position plus 1 is its left child, 2 times parent's position plus 2 is its right child. So 2 times 0 is 0 plus 1 is 1. 2 times 0 is 0 plus 2 is 2. That's a really bad 2. Now with D, its parent is 1. 2 times 1, 2 plus 1, 3. 2 times 1, 2 plus 2, 4, and so on and so on. And so you can actually see how children and parents are mathematically linked up when you're programming this way to stick it into an array. And you can decide about memory space with an array, because remember, at any given level, 2 to the n at any given level is the number of nodes. So if you know that you're going to have a tree of this size, you can easily locate the level of nodes that you need. Okay, so with that being said, let's run through kind of the tough operations of insert and delete. There aren't really any easy operations with heaps to understand because of this heap property, but it's important to know that this makes the runtime speed quick. So you keep the log n algorithm, but the complexity is slightly different in terms of programming. So what has to happen now, let's run through an example of inserting and deleting. So we want to insert an item. Now remember, we have to maintain the shape property, but we also have to maintain the right position. So, okay. So now let's insert a node. So when we insert a node, there's several different conditions. The algorithm always starts the same way. You always insert into the next position to maintain the shape property and keep it complete. So whatever you're inserting, you always insert it right there. And then you run a heapify algorithm on it. So first, before I run the complex example, note that it's not crafted this way. If this is less than G, then you don't have to do anything at all. You can simply detect that. But we're going to use a complicated example, and we're going to go with K. Now, K is out of position, because K should be all the way at the top here, because this is a max heap, so K is the largest item. So it needs to go up here. But again, we have to do this algorithmically because we can't just visually spot. It's not going to help you do the programming. So what has to happen is you run heapify on this. When your book runs through the programming details, it will run through the understanding part of it. You do swaps. Successive swaps up is all you do. So you always put it here, and then you do swaps. So is the parent greater than the child? And in this case, no, it's not. If it is, then you leave it alone, you're done. If it's not, then you swap them. So we swap G and K. So now this is K, and this is G. Now we do this successively, recursively, in fact, up the tree. So we check, is H greater than K? No, it's not, so we swap them. Now I put H here, put K there. And now is J greater than K? No, it's not, so we have to swap that. And now we put K up here and J there. And since there's nowhere else to go, we're done. Now, double check that this doesn't actually interfere with the order property. So K, is this greater than everything else in the tree? Yes. J, is this greater than everything on this side? Yep, looks good. And H, is this greater than everything here? Yep, still the case. Because when you're flipping the nodes up, because whatever you're flipping is always greater than, you never disturb the actual property. So at any given point, the property still holds, and that means no matter what the algorithm, how many shifts the algorithm does, the property will still hold for the entire tree. So this isn't too bad. This only requires log n steps because you're only going all the way up the tree in the worst case, like this. In the better case, it's already in the right spot, or you only have to flip once or so. Okay, now with delete, what happens is we always remove the top level item, remember, because it's the highest priority item. So we're always removing the high priority item. We never have to search or do anything special, but we do have to ensure that the order property and the shape properties are maintained. So the algorithm here is somewhat opposite of what we went through. What we do is we swap the top item with the last item in the array, which is the item that's furthest over on the very last line, which we recall as maps to the last item in the array. So K here, G here, and now we remove this. Highest priority item, remove it. Or you can do it the other way around, remove it first, then swap the spot. The point is there has to be a root node, right? But we're getting rid of this. But now we have to restore the shape property. I'm sorry, the order property. And now as we do successive swaps down. So we compare a parent with its children. And what you do is you pick the largest child if there's a swap that needs to occur. So G to J and I. We pick J because it's the largest one. Now we go down here and we swap these because J is in fact greater than G. And we have to pick the highest priority, the largest one in this case, a max heap, because it always has to be at the top, right? K was right. So now K, you compare that to its children. It's H-I-J-K, yeah, alphabet, right? It is, in fact, oh, I'm sorry. Getting tired. That was G. Okay. So G is swapped with J. And now we check its children. So is G greater than B or H? No, H is actually bigger, so we swap that. So now I move G down here with H. And now we have to again check its children, G and E. Is G greater than its child E? Yes, so we're done. But it might require one more swap in the worst case. And that's it. At this point, all the other, the order property is maintained, the shape property is maintained. So when you insert, you always insert in the bottom, flip to the top, and then reheapify down. And when you remove, you flip the other way. You remove the top item, move the last item into its position, and reheapify. And that's it for heaps.